Hi, welcome to me313, Mechanical Engineering Thermodynamics. The topic of this video is cogeneration, and the section in the textbook is 10.8. Here are the three learning outcomes for this video. At the end, you'll know the basic components of a cogeneration plant, you'll be able to define the utilization factor for that plant, and you'll be able to analyze and solve for all the conditions of a cogeneration plant. So let's look at a cogeneration plant, a very simple one, or what is often called the ideal cogeneration plant, and it looks just like what you've seen before with a Rankine power plant, except right over here where I've got something called the process heater has replaced the condenser. Again, we've got heat coming out, but instead of just dumping this heat into a river or some sort of thermal sink, we're actually using it for something, and so therefore we're changing the name to process heat. This tends to be used in, for example, large industries that have large heating loads to heat buildings, or maybe to go ahead and process the materials, preheat the materials that they're using. The TS diagram for this looks just like what we've seen for the simple or ideal Rankine cycle, because this process heater is functioning just like the condenser. In fact, as we have it drawn here, we're taking something that's superheated or maybe slightly a mixture and turning it into a condensed liquid. So it's functioning as a condenser. So the outlet of this would be 0.1 on this diagram as I've shown over here. So it looks just like the ideal Rankine cycle. And so this step right over here, which is 4 to 1, is where the process heat is happening. So if you go ahead and find the process heat, it's going to end up being the mass flow rate times the difference in enthalpy of 4 and 1. And we'll go ahead and see that a little bit more detail a little bit later. Now, the thing with the ideal cogeneration plant is that it's not very adjustable, and so it's always delivering a constant amount of heat. And if the plant needs different amounts of power, different amounts of heat, you can't adjust that very quickly. And so this is actually the way they tend to be done. They're a little bit more complicated, but now they're more adjustable. And so what we have now, the key part over here, is we have this throttling valve that we can go ahead and open and close. And that changes the amount of material that's going into my process heater. So here's the process heater at that point. So we still have a condenser in this case. And the process heater is here, and it's actually got two inputs. We've got this superheated steam that's just coming through a throttling valve, and then usually we take some off the middle stage of the turbine and we mix the two, and this is the process heater. It produces heat, and then usually the material becomes condensed so that we can go ahead and run it through a pump. So let's say it's a little more complicated. We have two pumps now. We've introduced the process heater. Throttling valve doesn't really add too much complication, and we've gone ahead and gone from a single stage turbine to a two-stage turbine. But as we'll see when we do an example here in a little bit, this can be dialed up and dialed down fairly quickly just by simply turning that valve. So let's go ahead and draw all the states on a TS diagram. And so on this diagram over here, I've drawn up the three isobars, because what you recognize now is that we've got three pressures. And so it'll help us to put all of our points on here if we have our isobars ahead of time. And so let's just go ahead and start with some of the points that we know fairly straightforward. Let's look at the outlet of the condenser. That right there will be 0.8, and it's going to go through the pump, and this goes all the way up to the high pressure. So 0.9 is going to be above it right over there. Okay? Let's look at the outlet of the boiler. That's another point that's pretty easy to put on. We know that that's going to be superheated at the high pressure, so 0.1 would be up there. And what we see is that there's this little fork in the pipe. Points 2 and 3 are the exact same as 1, so we'll just say that's 0.1, 2, and 3. And let's first look at the turbine. If this is an isentropic turbine, 3 to 5 to 6 just go straight down. So this point right there would be 0.5, and then at the lowest pressure turbine, that right there would be 0.6. Right. So let's go ahead and look at the throttling valve now. So we have 0.2, and it's going to go to 0.4. So we want to figure out what 0.4 is. And one of the things to recognize is that 0.4 is at the same pressure as 5. So this is that intermediate pressure. So that means 0.4 is going to be somewhere on that line. I want you to take a minute and think about where would 0.4 be relative, for example, to 0.2, which is right up here on that middle line. Well, if you remember from basic thermal, we talked about throttling valves like in refrigerators. This is an isenthalpic valve, so that means that the enthalpy is constant and it expands, and so 0.4 is actually going to be somewhere over there on that line. It's going to have a larger entropy, it's going to expand, but the enthalpy is going to remain constant as I move across. So that is where 0.4 is. We got 0.5 labeled. Let's look at the outlet of the process heater, which would be 0.7. If this is going to go into the pump, it's going to hopefully be a liquid. So we'll go ahead and have 0.7 there. We go through from the middle pressure to the high pressure 0.10. That's an isentropic pump. 0.10 will be right above it. And we're almost done here. This is a mixing chamber where we're at the high pressure. 0.9 and 10 is mixing to form 11. So we know that 0.11 is going to be somewhere in between. And it looks like we got everything labeled. So, all right, so that's what our basic TS diagram looks like for a cogeneration plant. Let's look at doing the energy balance over the process heater. So here I've expanded it here. So this is the process heater, and one of the things is we have that throttling valve. So this is where the valve is right up here. And so I'm saying we have some fraction of the mass flow rate X that is coming through there. And this is coming from the middle stage of the turbine, and we have some fraction Y. So both X and Y will be somewhere between 1. And so if we draw up our energy balance, what we know is that, well, the energy that goes in is going to be equal to the energy that goes out. And so the energy that goes in is going to be the mass flow rate times X, if I look over here, times H4. That's the stream coming in. We have that stream coming in there. So that's going to be the mass flow rate times the fraction Y times H5. And that is going to be equal to the energy going out, which is going to be Q sub P, the process heat. I'm writing this in a rate term, plus, and now X and Y times M, because X, the fraction X and the fraction Y added together, times H sub 7. So there's my energy balance for the process heater, and that's how I'm going to go ahead and get this value Q sub P. Next thing I want to talk about is something called the utilization factor. So again, I'll kind of return to this cogeneration plant where I have my process heater here, Q sub P. The turbine is generating some work, called that WT. The pumps are requiring some work, WP, WP1, WP2, and we have a heat input right over there, Q in, and our condenser, so we have Q out over there. Right? In terms of utilization, what we're looking at is our desired over required, and actually we have two desired products here. We have the process heat and the turbine work. All right, what's required is Q in, and then we're also requiring this pump work. So if we go ahead and talk about the network right over there will be the turbine minus the work of the pump 1 minus the work of the pump 2. That's the minus sign right there. That would be the net work. And so the desired is going to be the network and the process heat. And that's what's called the utilization factor. So I have it written here using the notation of the textbook. And again, desired over required, W net plus the process heat over Q in. And again, to get the net work, it's easiest to go ahead and just calculate the individual components of turbines and the pumps. All right, so we're going to do an example. What I'm going to do is, this is actually the example from the textbook, but we're going to do it in EES, and we'll look at it in a little bit more detail. So we just kind of mentioned briefly some of the main points. The high pressure is 7 megapascals, and we're given the boiler outlet at 500 degrees Celsius. Our middle stage pressure is 500 kPa, and our condenser is operating at 5 kPa. And then there's a fraction X that's going to come in here, and a fraction Y, and in the textbook, this fraction is 0.1. Sorry, Y is over here, and that fraction right over there is 0.7. So this is, again, the example from the textbook. So let's go ahead and solve this in EES. All right, so here I have it in EES, and so I'm going to step through like we've done before. So I'll go ahead and start off with what's given in the problem. So up here at the top, I have my high pressure at 7 megapascals, at boiler temperature of 500 degrees, my middle stage pressure of 500 as well, and then the low stage pressure at 5 kPa. I'm specifying that the outlet of the condenser, which is 8, is going to be a saturated liquid, and then also the outlet from the process heater is going to be a saturated liquid, quality of 0. And the problem also gives the mass flow rate at 15 kilograms per second. And again, there's my fractions going through the valve, which is 0.1, and the mid-stage turbine, which is 0.7. All right, we can, a couple other things we know, because there's those 3 isobars, so we can actually just go ahead and specify those pressures. So at the high pressure was 1 and 2 and 3. In fact, those were all the same point, if you remember. So those pressures are all the same. Again, I've written them on the same line with this semicolon just to kind of conserve space. And then we also know that the inlet to the boiler is also at a high pressure, so that's point 10, 11, and 9, that's the mixing chamber, and all those pressures are the same. Those are all high pressure, so both those lines there are high pressure. Our middle pressure is points 4, 5, and 7, so those are specified there, and the low pressure, which is 6, is the same as 8. So if we solve this, oops, not that window. We look at our array window here, we see now we've got pressures at every state, and the other things that we've known is the temperature, and we know the quality. So what we can do now is we're going to start kind of stepping through to fill in some of the rest of the lines. So if we go and look at our diagram, let's return to the diagram of the problem here and look. Okay, so what we know is we know this point up here, which is point 1, and we know point 8 and 7. We have two variables at that, because we have the saturated liquids at 8 and 7, and this we had a temperature and a pressure pair. So now what we're going to do is we're going to connect these vertical lines. So we're going to get 0.9 from 8, saying it's isentropic, 10 from 7, saying it's isentropic, and then 5 and 6 as well from saying that it's isentropic. So returning to EES, let's go ahead and come down here, and I'm going to uncomment a few more of these lines here. All right, so let's go ahead and first look at what I have written. This is my isentropic pump. We knew 0.8, so I'm just having EES find the entropy value, making it isentropic. And then I'm going to do the same thing for the other pump. Those are what those two equations are. My isentropic turbine, so I find 0.1, and that's going to be the same as 5 and 6. And remember, points 1, 2, and 3 are actually all the same. So there's where my three entropy values are. Okay, so now if I look at my table, that filled in a whole lot. Now I've got P and S at almost every point, except I don't have it quite at point 4 yet, or point 11. So let's look at what those points are again. Okay, so we need point 4 and point 11. So let's first look at point 4. Point 4, remember this is an isenthalpic step. So what I'm going to do is find the enthalpy up at this point up here at the top, and then just set that the enthalpy. So actually what I'm going to find is going to be the enthalpy at point 4, just because it's going to be up here. That's going to be my second intensive variable. And then let's look at the other thing we're going to do. Point 11 was the other one we needed, and that's over the mixing chamber. We're going to do an energy balance, mixing 9 and 10 to go ahead and find 11. So those are going to be my two equations that I'm going to add now to EES. So let's go ahead and look at this now. All right, so here I went ahead and I had that throttling valve that was isenthalpic. So there I found the enthalpy at point 1 and just set that equal to 4, right? And then I have my mixing chamber, right? And so there's my energy balance over my mixing chamber. My inlets are 9 and 10, and the outlet over there is going to end up being equal to 11. And then I'm going to go ahead and just find the remaining enthalpy values. That's why I have this duplicate statement, 5 and 10, and I'm missing 2 and 3, so I just added those as separate lines. The duplicate only saves a marginal amount of space here at this point. So now if I go ahead and look at my table, what I realize is that I'm able to get enthalpies at every single point now, and that's really what I'm going to need to solve my problem. So although I don't have an entropy at 4 and 11, I'm actually not going to need it. The numbers that we really care about are going to be the enthalpy. And I have it at all 11 states now, so my problem is more or less completely solved. So let's go ahead and just start solving for some stuff like the process heat and the utilization factor. Okay, so here's my next set of equations. Process heater, and we looked at this energy balance already. The inlet was H4 and 5, and they're weighted by their mass fractions. And this is the outlet. So I'm doing this all per mass, and then what's coming out is the process heat. We go ahead and look at the network that's coming in. Actually, I shouldn't call that network. That should be called that turbine work. So we call that turbine work. There we go. All right. So this is actually turbine work. And so this is my energy balance. And it's actually, let's go ahead and this turbine energy balance isn't necessarily straightforward. So let's go back and look at our turbine. So we're doing an energy balance over here. So it helps to think in minus out. And so I have what's coming in here, but this is, I've already removed the fraction x, so I've only got a fraction coming in here. And then I've got an outlet there, an outlet there, and an outlet there. And so I've got a fraction y coming there. I have a fraction 1 minus x minus y coming out in the bottom, and then my net work. So let's go back and look at that energy balance that I had, that I have written. And so I have in equals out, so in 1 minus X of H3, that was the inlet, and it has those 3 outlet streams. The middle stage pressure, then I have the low stage pressure, and then the turbine work. That's going to go ahead and give me the turbine work on a per mass basis. And then my pump work, well, these are my 2 pumps. This is a 1 minus X minus Y. That's my larger pump that could be outlet of the condenser. And then this is my mid-stage pump. And then I can find the heat input. That's simply the difference between 0.1 and 11. So now I went ahead and have all my, excuse me, I have all of my work equations and heat equations. And you can see those a little messed up there. There we go. We can go ahead and see we've got various values of heat and work, process heat, the amount of heat going in. We can do a sanity check, make sure process heat is less than the total heat input. You see the pump work is actually pretty small. One of the things about Rankine cycles is it doesn't take much work to pressurize liquids. And so now let's go ahead and just solve for the utilization factor. That's my last point. All right, so first let's look at the equation for utilization. The net work, turbine work minus the total pump work, and utilization, desired or required, net work, process heat over the heat that goes in. And so I look now at my utilization factor. My utilization factor is 0.865, so I'm using about 86.5% of the energy that I'm putting in for something that's desirable. Now there's a couple things we can do. Let's look at this a little bit more and find out, for example, we'll use ES here, like what would be the effect of opening and closing that valve? So remember, if I want to look at the effect of something, I'm going to comment that out and then create a table. So I'm going to comment out X, which is 0.1. That's the fraction going through the valve. And I'm going to go ahead and create a table. And so we're going to go ahead and vary the value of X. And let's look at how that affects things like the utilization factor, about the amount of process heat. So we'll go ahead and look at the amount of process heat. And let's look at the network. Okay, so let's look at X, and we'll go ahead and have that go from 0 to 0.2, and our problem was 0.1, so we're going to go look at 0 to 20%. All right, so let's look at what's in these trends here. As we go ahead and open the valve, so opening the valve is making X larger, we realize our utilization factor becomes larger. The process heat goes up, which we would expect because we're putting more steam into the process heater. The network goes down. That makes sense because we're decreasing the amount of material going through the turbine. The one that may not be entirely obvious was that the utilization factor goes up because you're increasing process heat and decreasing work. But remember, it's easy to go ahead and convert heat into something you want because you don't have to a second law efficiency there. So you're actually, by using more process heat, you're actually increasing the utilization factor. Okay, so let's go back to our slide here, and I think that wraps up this video.